Welcome to In 5 Minutes. The agenda of this clip is to continue our understanding on supply voltage scaling. We know that the objective of supply voltage scaling is to scale a supply voltage without compromising on the performance. And we saw some of the techniques for the same in the last clip, which was nothing but static voltage scaling, multi-level voltage scaling, dynamic voltage and frequency scaling. Let's understand the approach to each one of them into a bit more detail. So the approach to static voltage scaling is what we'll discuss. The first approach is the feature size scaling. As we know that the technology is scaling down, right? The length of my channel is getting reduced. We have also studied scaling in details previously. With the technology being scaling down, the processes are improving, the width, the length, the supply voltages and the terminal voltages being scaled down. We know that when VDD is scaled down, our dynamic power dissipation will reduce. But we also know that the feature size scaling means the terminal voltages, one of which also is the threshold voltage. When that is reduced, we know that the subthreshold current would increase exponentially. So there's a limitation on reducing the threshold voltage, but with the device or with the feature size scaling of the device, we can definitely reduce our dynamic power dissipation without degrading the performance. But once subthreshold current comes into the picture, the designing becomes quite a challenge. So this is just a simple understanding that when VDD is scaled down means VDD is equal to VDD by S, where S is a scaling factor greater than 1, then I can have fixed voltages as we discussed in the previous clip, and that's nothing but the static voltage scaling. The other one is a very interesting one. It is at the architectural level, which is nothing but through a concept of pipelining. I can also explain you this with the concept of parallelism, but let's understand it through pipelining. So suppose this is my block. I'll translate this analogy to digital circuits soon. And there are 5 particular people who need to do some task, and each of them take 2 nanoseconds, and each one of them is dependent on the previous person to start his task. That means if A, B, C, D, E all are taking 2 nanoseconds, then finally, say at 0 time when I started, I will get my output of E at 10 nanoseconds. If I would translate it to digital circuit, that means in a time period of 10 nanoseconds, the time period of 10 nanoseconds, all my blocks which are performing sequential operation and dependent on the output of the previous stage will complete its computation and have my final output ready. That means a new output will come after every 10 nanoseconds, and I can take a new input also after every 10 nanoseconds. In order to reduce this time period, what we do is we partition all these blocks, and in between these blocks we put some registers which operate on clock. Now what's going to happen is we technically know that each of this guy is going to take 2 nanoseconds to complete its computation, correct? So let's say I have task 1, 2, 3, 4, 5. So when I start the computation, my task 1 will go to A, correct? At that point of time, all these people are not doing anything or are producing garbage at its output. In the next 2 nanoseconds, this task 1 will go to B and task 2 will go to A. This time these 3 are idle. So after the next 2 nanoseconds, that means I have technically completed 4 nanoseconds. My task 1 comes here, my task 2 comes here, and task 3 will be taken here. After the next 2 nanoseconds, task 1 here, task 2 here, task 3 here, task 4 here. And after that, task 1 here, task 2 here, task 3 here, task 4 here, and task 5 here. After I complete 10 nanoseconds, I get my first task ready at the output. Same like what we discussed here as well. But understand what's happening here is another 2 nanoseconds, which is 12 nanoseconds, my task 2 is also ready at the output, which was not the case here. Here my task 2 would have come in 20 nanoseconds, correct? Here task 3 will come in 14, because in another 2 cycles 3 would come at the output, then another 2, 4 will come, so at 16, another 2, 5 will come, so in 18 nanoseconds. So though each task will take 10 nanoseconds to complete its computation, because all of these tasks are happening parallelly, which is nothing but pipelining concept, which increases the rate at which the output is produced. At every 2 nanoseconds I can produce a new output, and this is nothing but the throughput which improves the performance.